Olivier Bénichou. Yeah, and he's the director of research of the Scientific Research National Center, France. And he was a postdoc at the Laboratory of Theoretical Physics and Statistical Model, and a PhD at the University of Paris. Yeah, also did military service. So a scientist. Yeah. He's over there.
Okay, thanks a lot. So first of all, I would like to thank the organizers for the invitation to this conference. So the results I would like to present to you today have been obtained in collaboration with several people, with Léo Régnier, with the PhD students in the group, with Maxime Dolgouchev, who's here, and with Sid Renaud. So the type of questions we've been interested in is the following: how to characterize the efficiency of space exploration by random walks. So this is, of course, a very general question, but it is usually quantified by the number of distinct sites visited after t-steps, which is also called the range of the random walk. So on this example, you have a 2D simple random walk, and the range is simply the number of black visited sites at time t. N of t, the range of the random walk, is actually a standard observable of random walk theory, and it has generated a huge number of works. For instance, you can calculate the average of n of t, the variance of n of t, and even the full distribution in one dimension, and that's the rescale process in higher dimension. So n of t is a very important observable. One of the reasons why it is so important is that it has many applications in a variety of situations. At the macroscopic scale, one example is provided by so-called foraging theory. So here, you represent schematically a forager by a simple random walker, and you imagine that initially, all the sites of the lattice contain 1 unit of food. Each time that the random walker meets a given unit of food, it is consumed. So finally, n of t quantifies the amount of food collected, and this is efficient to quantify the efficiency of the forager itself. At the microscopic scale, an important example is provided by the so-called trapping problem. This time, the random walker represents a molecule that diffuses in a given medium, and each side of the lattice contains a trap, which is fixed in space, and this trap is present only with a given probability p. People have been interested in the so-called survival probability, the probability for the molecule not to have met any of the traps at time t, and it is easy to realize that this quantity can be written like 1 minus the concentration of traps at the power, the range, average over the realization of the traps. So if you are interested in the kinetics of the trapping problem, you have to be able to calculate the distribution of the range. So finally, the range is theoretically important, and it has many applications at various scales. However, the range at time t provides only limited information on the dynamics, and I think this is best appreciated in the context of foraging I just mentioned. Actually, a forager may visit the same number of sites, but in very different ways, and this is just because n of t is an integrated quantity. So here is a first realization of a trajectory of the forager that leads to a given amount of funds collected at a given time, and a second trajectory leading to the same amount of food collected at the same time. But in the first case, resources are found almost regularly, while in the second case, you have a very long period of time during which no food is collected. So this discrepancy can have dramatic effects in foraging. The first forager is likely to survive if it has to eat on a regular basis, but not the second. So if you want to understand this disparity, it requires the knowledge of new random variables. These new random variables are the times between the visits of new sites, tau n, typically this type of terms, and this is typically what I would like to discuss today. So more precisely, I will define tau n like the time elapsed between the visits of the n's and the n plus first new sites, and I will denote by Fn the distribution of tau n. Just to settle things, let us consider specific realizations. So here, I assume that the number of visited sites is 30. These are the black sites. The green site corresponds to the boundary between the visited and the unvisited sites. In blue, I represent the nth site visited here, and in red, the n plus first new site visited. And it takes 1, 2, 3, 4, 5 steps to discover these sites. So that tau 30 is equal to 5 in this case. So technically, if we want to determine Fn, what you have to do is to solve an exit time problem, as we heard this morning, but this time, the random domain that you consider is random and not given a priori like this morning. And in addition, this random domain is generated by the random walk itself. It is not put by hand. This is generated by the random. This is a complicated problem. In the case of a two-dimensional random walks, we know that the support of the random walk contains holes, islands, very complicated at all scales. Yes?
Just a quick question. If you think about the energy landscape with multiple local minima, could we interpret them as sites in this sense and ask, like, if it has limited n local minima, then
No.
plus first local minimum or
Not really here. This is completely flat energy landscape. In the first part, at the very end of the talk, I will say a word about this part. But here, this is completely flat. Okay?
in the origin case, can we not think about like where the food is like a minimum and then
Okay, of course, you can think of more complicated problems, and we will try to think, but let us start by the simple random walk case, okay? I think that already this problem is complicated because of the geometry of the random walk, okay? I will come back to this point at the very end of the talk. And what I would like to do today, and this will be very simple, I will use only scaling arguments, and we'll try to show that despite the complexity of this domain, the statistics of tau n obeys actually universal statistics. So I will start from the example of very simple one of a one-dimensional simple random walk, because in this case, even if the tau n had not been considered, everything is implicitly known. So in this case, once you have visited n sites, because there is no holes in the domain, the problem is very easy. The only thing that you want to determine is the first exit time probability of an interval of size n, starting from one that is set from the boundary. And of course, this is a well-known quantity. You can in particular analyze this quantity in the large n limits with tau divided by n squared fixed, n squared because we have to do with regular diffusion here. And what you find is the following. And from this explicit expression, we can draw several conclusions. So first point, you have aging in the problem in the sense defined by Hart previously. As we can guess, Fn depends explicitly on n. This is, of course, expected. Second point, even if it depends explicitly on n, at small times, you have an n-independent algebraic decay. This is also expected. If you consider small times, you do not even know that you have a finite domain. And you end up with the expression corresponding to the semi-infinite problem. This is a well-known algebraic decay in the semi-infinite case. This holds true as long as the random walker has not crossed the interval, which occurs at a timescale n to the square. After which, you end up with an exponential decay, also expected because this is a finite system. And last point, over the whole timescale, Fn admits actually a scaling form, which is the following. The question now, what happens in higher dimensions? Which of these features still holds? And this is a priori complicated question again, because the territory is a complex object. And second question, what can be said for general random walks? By general random walks, I will define them later in the next slide, but I have typically in mind random walks leading potentially to subdiffusion, like can be the case in the cells, as we heard from Hart previously, or on the contrary, superdiffusive random walks in the case of Levy flights. This is typically what I would like to discuss. So by general random walks, I mean the following. So we will consider symmetric Markovian random walks, and I will restrict myself to discrete times. I will also assume that we have a scaling variance hypothesis for the infinite space problem, meaning that we can introduce two dimensions, as we heard this morning in the talk of this morning. So let me just remind the definition of the two dimensions I will use, the fractal dimension of the system and the dimension of the walk. So let us consider this medium. This is the medium on which the random walk will evolve. We will draw a circle of radius r in it, and we will ask two questions. So first question, how many sites of this structure are contained in this circle if this number of sites behave like a power law, this defines the fractal dimension of the medium. If we consider a Euclidean regular lattice, this is simply the Euclidean dimension, purely static quantity. Now we put a random walker at the origin of the circle and we ask a dynamic question. How much time does it take this random walker to exit the circle by any point of the circle? If this time behaves like a power law, this defines this time the dimension of the walk. For instance, for regular diffusion on a regular lattice, dW is equal to 2. So with the help of these two dimensions, you can construct the ratio mu dF divided by dW. And this determines the type of the random walk. If the random walk is recurrent or transient. This is well-known fact. If mu is strictly smaller than 1, you have a recurrent random walk with probability 1, it comes back to its starting size. If mu is greater than 1, this is a transient random walk, and you have the marginal case in between. And mu is dF divided by dW. Okay, excuse me, dF divided by dW. And this type of the random walk, recurrent, transient, or marginal, is actually crucial to answer the question of the times between visitations of new sites. Actually, what we find that in recurrent cases, you find exactly the same phenomenology as in the 1D cases, excuse me. You find an algebraic behavior at small times and an exponential regime at large time, and you have a scaling form for Fn. In a transient case, this is very different. Now, at early times, you have a stretched exponential regime, followed by an exponential regime, and you do not have any scaling. In the marginal case, you have a combination of both. You have 3 regimes, actually, algebraic, stretch exponential, and finally, exponential regimes. More precisely, you can actually classify everything. You obtain the dependence of the cross of the time between all these regimes as a function of n, the number of sites already visited. You obtain the exponent of the algebraic regime I described here. You obtain the exponent of the stretched exponential regime. And actually, I claim that this is very general and applies to processes very general. For instance, regular diffusion in D dimension, anomalous diffusion, both sub and super diffusion, and diffusion in disordered mediae and fractals. I just would like to show you, before giving some words about the technical tools we used, illustration of this. So first, you can consider the recurrent case and illustrate it first by the case of one-dimensional Levy flight. So this random walker jumps with this distribution, a large distribution. This is the so-called arrival convention, meaning that only the arrival site is visited, not the sites in between. And if alpha is comprised between 1 and 2, you are super diffusive, but in the recurrent situation. You can also consider the example we heard about this morning, a random walk on a deterministic fractal, here, the Sierpinski gasket. So this time you have a subdiffusive behavior, and you're still in the recurrent case. Finally, you can also consider a random walk, this time on a random fractal. Here, the example is given by a 2D critical percolation cluster, which leads again to subdiffusion. And in all cases, you check the algebraic decay with the exponent we predict, an exponential decay, not shown here, and a scaling behavior, which is shown by the delta collapse on this slide.
So in the last case, mu is random.
Yeah, I use what?
In the last case, mu is random. Almost
it's
a random fractal.
Yes, it's a random fractal, but mu is well determined. You know df, you know dw, you know mu.
They are like deterministic numbers.
Absolutely, deterministic numbers.
The scaling function is it the same or it's
No, it is process dependent. It is process dependent, the scaling function. Other questions? So let us turn to the transient case. So this time you can illustrate it first by the 3D simple random walk example. So here mu is indeed greater than 1. And you check first the stretch exponential regime. Indeed, this plateau regime with this choice of the coordinates corresponds to the check of the stretch exponential we predict. And then we have the exponential behavior. You can also test it with the example of a 3D persistent random walk. So persistent random walk, you have a probability to go in the same direction as the previous step. So you just have the memory of one step, not like the fractional Brownian motion we heard about previously. And finally, you can also illustrate it by the example of a 2D Levy flight with any value of alpha between 0 and 2, which leads to superdiffusion. And again, you check the stretch exponential behavior we predict and the exponential decay. Finally, the marginal case, you can illustrate it with one-dimensional Levy flight in the marginal case alpha equal to 1. You can illustrate with a 2D persistent random walk, and finally with a very important example of a 2D simple random walk I gave in the introduction. And in each case, you have the algebraic decay tau to the -2, stretch exponential behavior, and an exponential decay finally. So finally, for a very large variety of examples, you check the predicted result. So I now would like to give some words about the tools we used. Again, only scaling arguments. The first step consists in a mapping between the visitation process we consider here and the trapping problem. This mapping is as follows, it's very simple. You realize that the unvisited sites in white here act as traps for the random walks. Very simple, almost by definition. But in contrast to the classical trapping problem, two very important things. First point, the spatial distribution of traps ages. It is constantly updated by the visits of the random walks. And second point, these traps are spatially correlated. And again, the correlation is not put by hand, but generated by the random walk. So this is very different from the classical trapping problem. Next question, is it possible to say something about this traps distribution? Actually, as in the classical trapping problem, a very important quantity is what I denote by Qn of R, the distribution of the radius of the largest spherical region free of traps, typically this quantity in the visited domain. And what we've shown, that this quantity satisfies this scaling behavior with A is a constant and rho n provides a typical scale of this radius. And in fact, you can determine the n-dependence of rho. What you find is the following. In the recurrent case, rho n is proportional to n, the volume of the system, at the power 1 divided by df. This is not unexpected, because in the recurrent case, we expect a kind of compact exploration with almost no holes in the domain. So this is a reasonable estimation. In the transient case, you find also something which is more or less expected, because you have many holes in the domain. You can think that you have a region that does not scale with n, and this is what we indeed find up to log corrections that are not precise here. Which is striking, I think, is what we find in the marginal case, where you have a new length scale, which is the square root of n to the power 1 divided by dn. This I do not know how to predict in advance. So now that we have this, we can say many things. Step 2, we can say something about the early time algebraic regime of recurrent random walks. This is a very simple approach, and it works as follows. Because we consider early times, we have indeed a region type problem in an effectively infinite region. This is similar to what we did in 1D. At small times, we can forget some part of the confinement. This is exactly what we did, and this is why I denote by f infinity this quantity independent of f. So how do we obtain it? 3 ingredients are actually needed. First ingredient, we need a renewal equation between the quantity we are interested in and the probability to be on a trap at time t. This renewal equation is as follows, written with continuous notations for the sake of simplicity. It just tells you that if you want to be on the trap at time t, either you go on it directly, or you can partition it over the first time you visit this region of traps. And after, you want to be back in the remaining time t minus tau on this trap region. And because this is a Markovian process, you can forget everything about the past. This is, of course, a mean field type equation. You forget everything about the position of the set of traps. They are treated, these traps, only collectively. Second step, we have to say something about p trap of t to be able to say something ultimately about what we are interested in, f infinity. And what we say, very simply, is that the random walk is almost uniformly distributed in a sphere of radius r of t, proportional to t to the power 1 divided by dw, by definition of the dimension of the walk. Next step, we have to count how many traps are in this sphere. And by definition, it involves this time the fractal dimension of the set of traps. I would say we're just after about this quantity. But if we suppose it's known, we can say that the probability to be on a trap at time t is simply given by this ratio, number of traps divided by number of sites. Finally, it behaves this way with time. The last step consists in determining the fractal dimension of the set of traps. And we have done it. You can show that this quantity is given by 2df minus dw. Now we have everything, and you can obtain the algebraic behavior I gave you before for the recurrent random walks. You can also obtain the first cross of the time. It is obtained by the crossing time of the radius rho n of the largest region free of traps at the power dw. So now we know everything about the first regime of the recurrent random walks. Last step, I would like to say a word about the intermediate and long time regimes. So they can be obtained by paralleling what is known about the classical trapping problem. So it consists in constructing a lower bound for the survival probability, and by assuming that this lower bound actually provides the correct time behavior of the survival probability. So how is it constructed? It is constructed by noting that it is controlled by the rare configurations of the largest spherical trap-free regions, and we know the corresponding radius distribution calculated earlier. So finally, the lower bound works as follows. If you want to survive, a very simple way is to say that you have a given region free of traps, and you do not leave this region up to time t. This is what is written here. Here, Qn is the probability to have survived the first regime. Then this is the probability to have such a region free of traps. And finally, the probability to remain inside the sphere, which is a well-known object. Finally, you can estimate the large time behavior of this integral, and two possibilities can emerge. At small times, intermediate times, actually, you find that this integral is controlled by a value of r inside this interval, and you end up with a stretched exponential decay of Sn and finally of Fn. This is what I gave you in the introduction. At largest time, it happens something different. This value of the integral is controlled by the value of r outside of the integral. So it means that it is controlled by the upper side of the interval. And finally, you end up with an exponential decay of Fn upside. So very schematically, this is how you obtain the stretch and the exponential behavior I gave you previously. Just before concluding, I just would like to make a remark and giving you an extension. So first point, a remark. I think it is instructive to compare the algebraic decay we found to the usual persistent decay. So the algebraic decay of the recurrent case we found is this one. The decay of the first passage time to a single target in infinite space defines what is called as the persistent exponent theta. And this is something that has been studied a lot. And in particular, for processes with stationary increments, you can show that theta is given by 1 minus mu. So now you can want to compare both. And as you can see, if we rewrite mu in terms of theta, they're actually very different. They do not even have the same monotony with respect to theta. Just to say that this is very different from the persistent exponent, the exponent we found. Second point, we could be interested, to bounce back on the question I had at the very beginning, on possible extensions to these results. They have been obtained for Markovian processes. How can they be extended? So we can try bluntly to extend them to non-Markovian processes. Actually, they work for Levy flights with the crossing conventions, different from the one I gave you. If you find all the sites in a single run, and for this process, you cannot write a renewal equation. However, this result works. It also works with Levy walks, same type of works, but this time you count time differently. But importantly, it works for very non-Markovian processes. We heard that it's very difficult to determine first passage times for fractional Brownian motion, but actually this algebraic decay we predict, it holds, it is true, it seems to be true at least, for one-dimensional fractional Brownian motion, both in the subdiffusive and in the superdiffusive regions. It's also for the so-called true self-avoiding walk. So this time we have a random walker that deposits signal along its walk. So in this true self-defining walk, you assume that the probability to jump on a site I is a function of the number of the times the site has been visited. More precisely, it decays exponentially with this number of visits. So it is a kind of landscape you mentioned previously, even if specific, and it also works in this very non-Markovian situation. So I have no explanation for that for the time being. This is just a constatation. It seems to say that this result is very general. So finally, the times between visits of new sites are useful to quantify random exploration. For symmetric Markovian random walks, the distribution of these times obeys strikingly universal statistics. The only arguments I gave you today are only scaling arguments. They apply to processes as varied as regular diffusion in D dimension, anomalous diffusion, both sub and super diffusion, and diffusion in disorder mediate and fractals. And finally, I would like to stress that in addition to their intrinsic fundamental importance, I think that these time between visits are technically useful tools to analyze different problems. For instance, I think they can be useful to reanalyze the old question of the range of the random walks. For instance, you can be interested in time correlation functions. This is a study that has been initiated by my friend Gleb Shamin. He calculated the covariance of the range for a one-dimensional random motion. Actually, you can go beyond and you can determine with these tools all the correlation functions, and you can go beyond the Brownian motion. A second example of application concerns the natural observable of foraging theory I mentioned in the introduction. You can be interested in this problem of a random walker that has to hit at a regular rate, not to die, not to starve. And from the formalism we have developed here, we can determine the lifetime of such a two-dimensional starving random walker. So I think this could act as a promising tool to analyze several properties of random walks. So I just would like to conclude by thanking again my collaborators, by thanking you for your attention.
So maybe I missed it, but could you comment again on whether you think that one could go from flat surfaces to energy landscapes, maybe?
Maybe this is not what you had in mind, but in the last example of the true self-avoiding walk, we imagine that the random walker deposits a signal, and you have the probability to jump on a site that is a function of the times a given site has been visited. So this specific energy landscape, actually we can construct several other types of random walks, of this self-interacting random walks, they are called. It seems to work.
This would be then energy landscape which changes.
Absolutely, this is updated. It's updated with time and with the random walk itself.
Do you think this frame one could also look at the case where there's like some kind of fixed landscape below?
I hope so, but it's very recent work. I don't know. Honestly, I don't know. I can't say.
Thanks.
Scared of asking questions. I've seen some papers showing that lady flights are open for like foraging in terms of like when the food is sparse. And I'm not sure if you are familiar with that.
Actually, I am a little bit, actually. I can comment on this point. Several things. This is a long story, actually. This original article, they say, they claim that they study the following problem. This is a Levy walk, so Levy flight, but you spend time during a given flight. You consider a given repartition of targets, and you're interested in the number of targets found after a given time t. And you want to know if you can optimize this number with respect to the index characterizing your Levy flight. Actually, yet there is an optimization. In the case where the targets are found and disappear, the usual case, the best strategy simply is to go straight lines. So no Levy flight strategy. If you want to have an optimum, this is a very specific situation. Every time you meet a target, it reappears instantaneously at the same position. In this case, you have a kind of optimization. First point, the optimization is very specific. And second point, the calculation at the time was not really correct. You have to do it in a different way. The optimization is real only in 1D. This is the basic point. Otherwise, you do not change the scaling with the distance between targets. It was very important in the community because it triggers many very important studies. So I think it's very important, but you have to use this result with a lot of care.
I can comment on Olivier's comment very briefly. There's only one kind of toy model that I know where I'm sure that it's really beneficial and it works, and it's a pseudo one-dimensional model. Think of a long polymer, and you have loops in the polymer. The loops have power law distributions. If you jump along the shortcut, you can map it on the real level flights. Here, you don't need the speed because the jump is very short in space. And there, indeed, when you come to the real limit, it's a cushion. But of course, yes, it's replenishing target. I mean, your target is always new. But that's the only model where it can say with confidence. Otherwise, all these claims, they always rely on the other point somewhere out here. Is it real? Is it not real?
I look at some of the abstracts, they say it will be proven that many animals search for
Yes.
and live lives and their animals. Oh, like.
Yeah.
Of course, you can't look bad. It's a page to paper, but I didn't understand it possibly because they claim that lady walks out in bed, blah 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 blah. But then, and they published the paper in Nature. But then they realized that they simply misinterpreted the data from biology. And they published the second paper in Nature, which that you should have lady, but then it should be truncated in Spanish. They published the third paper in the Nature with a biologist now, Marinda, on the dynamics of sharks, of the biologists. And realize that there are some others. But you can also understand that if you're embarked on flying a long distance, it's not very economic way of searching, because you spend a lot of time flying. And then they realized another thing, that actually the data from biologists with alphabets was also very wrong, because they put the meters on the level of which were emitting only when they were flying. And then when they look at the data, they realized that the flight of 48 hours, 52 hours possible. And they didn't significantly count that sometimes they are in the mist. They are listening. And they prefer this flight.
It's a mess, but it was.
Okay, let's make the sticker again. Voice.